Hey there, let's do some calculations now using calculating exponents where we have non-prime modulus in them. Okay, and we're going to take a look at how Euler's theorem works here, which is essentially it's just a generalization of Fermat's little theorem. So we'll take a look at that. So let's start with the problem 13 to the 24th mod 36. Clearly 36 is not a prime number. I think we're all clear on that one. What I would suggest doing first is to calculate phi of the mod, the totient function. So what I'm going to do is phi of 36, and I need my prime factorization of 36. So I'll do phi of 2 squared times 3 squared. Okay, and if you remember in the previous video or a previous video where we looked at the phi for non-prime values, the way that works out is we take the first prime and we subtract 1 from it, and then we multiply that times the prime and then 1 less than the exponent that's given, so 2 to the 2 minus 1. And then we do the same thing for the next prime. We multiply that by 3 minus 1, and then times 3 to the 2 minus 1, okay? And so that's going to give us 2 minus 1 is 1, 2 to the first is 2, 3 minus 1 is 2, and 3 to the first is 3. So 12. So we get that the phi of 36 is 12, okay? The next question we need to ask is 13 a reduced residue? And so the easiest way to check that one is GCD again. So we are going to look at the GCD of 13 and the mod 36. And in this case, yeah, it's pretty easy to see that they're relatively prime. And so we know that the Euler's theorem is going to apply. Now, the nice thing about Euler's theorem is that it, like I said, a generalization of Fermat's little theorem. And so where that was the case of a number to, if we raised a base to a number that was 1 less than the prime mod, then it equaled 1. Well, in the case of Euler's, we know that it's a number n raised to the totient function of the mod. And I'm using p, but in the case, don't really mean it to be a prime number. Okay, so this is essentially what Euler's function is telling us, or Euler's theorem rather is telling us. So, which is nice because now I go back to the problem of 13 to the 24th, and I can go ahead and say, okay, well, I know 13 to the 12th because phi of 36 is 12 should be 1, and just to do all this stuff, it should be 1 mod 36. Well, unfortunately, arithmetic still works normally, so if I want 13 to the 24th, that's the same thing as 13 to the 12th, and I'm not saying the bars, and I'm probably going to drop right in for a little bit just to make that easier. Squared. So we already know 13 to the 12th is 1 squared, so that's just going to be 1. Fairly straightforward, right? And like I said, I'm going to drop the bars going forward. Okay, so straightforward application of Euler's theorem, reduced residue works, we found the phi. What if instead of 13 to the 24th, we want 13 to the 25th mod 36? Well, that's easy. Don't do the work. There's no need to calculate out 13 to the 25th. We know what 13 to the 24th is. So I can go ahead and rewrite this as 13 to the 24th times 13. And again, I'm dropping the bars. 13 to the 24th we saw in the previous part was 1 times 13, which is just 13 mod 36. Piece of cake. What about if we try 13 to the 26th mod 36. Well, we're still going to have to do some calculations occasionally that are not super simple, but there's nothing complicated about this. Based on the previous problem, we know that 13 to the 26th is the same thing as 13 to the 25th times 13. And like I said in the previous part, we saw that 13 to the 25th was 13. So we'll have to multiply 13 times 13. A little bit of information about me. I was born on Friday the 13th, so 13 is my lucky number, so I kind of like this problem. 13 times 13 is probably the first square I learned when I first figured out what squares were. 169. And then I think, okay, we're in mod 36, so let's see, 2 times 36, 72, times 2 is 144. 169 minus 144 looks like 25. Okay, pretty straightforward. So let's do a slightly different problem. This time, how about we consider 35 to the 144 mod 216. Okay, so let's change this. So just like the last one, the first thing I'm going to do is calculate the phi of 216. You might note that 216 is just 6 times 36, so I'm basically adding another 2 and a 3. So when I do my prime factorization, I get 2 cubed times 3 cubed. And then using our formula for calculating phi, we get 2 minus 1 times 2 squared times, and I'm dropping that piece there, so 3 minus 1 times 3 squared, so that's 1 times 4 times 2 times 9, which comes out to be 72. Okay, pretty straightforward there. Is 35 reduced residue? Well, GCD of 35 and 216, we know the prime factorization of 216 only has the factors 2 and 3. 35 is 5 times 7, no factors in common, so yeah, GCD is 1, so great, reduced residue. So Euler's theorem applies. So again, I can go 35 to the 144, so my phi is the number I'm looking for now, so I can rewrite this as 35 to the 72nd squared, and so just like the previous problem, this becomes 1 squared, which is just 1. What's cool about this now, like 144 is a pretty big number, and again, like I mentioned in a previous video, like do not be plugging this into your calculator and trying to do these things, because your calculator will round things off and you will lose the correct integers, and so we don't want to do all that work. 35 to the 144 is a pretty big number, but what if instead I said, hey, what is 35 to the 144,000 mod 216? Well, I'm definitely not going to plug that in. I'm not even going to do that into Wolfram Alpha. Even if it does calculate, it's going to take a long time. It's going to be a very big number. But based on what we just did, we know that 35 to the 72nd by Euler's theorem is 1. Well, 72 times 2,000 gives us 144,000. So this is essentially just 1 to the 2,000. So it equals 1. And at no point did I actually have to multiply those powers out. Okay, in the next video we'll look at some repeated squaring to do some work as well, and yeah, take a look at the next one.